Welcome back, students. In this video we are starting the third lesson, current, electricity. In the previous two lessons we talked about charges and fields, then potential energy, and then capacitance. And in this lesson we will be talking about current, electricity. Okay, what is current? Current is the flow of charges. If charges start flowing, then we say that there is current. So current is charge divided by time. So the rate of flow of charge, that is current. But in the last two lessons, we talked only about the static condition of charges. That is, you bring a charged something near a conductor, and then what happens is that the free electrons in the conductor, they move from one position to another position, and then in the static condition, then an equilibrium is established, and then all the charges are concentrated either on the one side or the other side of a conductor and stuff like that. So that's what we saw. So in the static condition, there is no flow of charges. The charges are, kind of stationary on the conductor, on the surface of a conductor. There is no flow of charges. That's what I'm trying to drive at in the static condition. But then, how would you make charges flow continuously? That is the question. To answer this question, we just need to think about the transient condition before the charges become static. See what is happening there? There are free electrons in a conductor and they're moving inside the conductor. Now you bring an electric field, or you keep the conductor in the presence of an electric field. Then what happens is that all these free electrons, they experience certain force, and then they align themselves inside the conductor, so that the field inside the conductor is zero, and then the potential across the conductor is the same. All these two conditions are met when they do the alignment. But think about it for a while. They moved first. Maybe they moved very quickly to come to that position, static position. Initially they were at some position, randomly moving. Now, because of the presence of the electric field, they started moving and then came to a steady state, a static condition, where you can see charges distributed on the surface of the conductor. Okay? So there was a very short time in which they moved to come to the new equilibrium position. So they moved, that's the most important thing. Under the influence of a field, they moved, and then they came to a steady position where they did not move any further. So that is what you call as electrostatics, because the charges were at the static position. Right? This is what we are going to focus on, this particular part of this, the transient part. The steady state, they're stationary, but they moved in the presence of an electric field before they attained the steady state. Why did they move? Because the field was set up, and that was the reason. Okay? And then they try to nullify that field. Okay? So let me give you an example. For example, let me give you a case where you can understand this better. Okay? Let me take a conductor, a metal conductor. Okay? Something like this. Let's say this is a conductor. Okay? There are free electrons in this conductor. And let me say that I'm going to have a dielectric on this side. This is kind of positively, this side is positively charged for the dielectric. And then on this side, I'm going to have a negatively charged dielectric. There are two insulators I've got. Okay, so what is going to happen? Because of the presence of the positive dielectric, on the positive charges on the dielectric, the electrons will start moving towards those charges. The electrons in the conductor will start moving towards the charges. And then they try to neutralize those charges, right, on the dielectric. And the same thing will happen here. Because of the presence of the negative charges here, then the electrons will get repelled in this, from this side, they start moving there. And they will try to neutralize, right? So in the steady state, they would have neutralized those, that field, and there would not be any further movement. These charges will also be neutralized. Positive will get electrons there and get neutralized. Now will become neutral again. Suppose that I'm going to make this neutralized charges, being present again. Suppose I have a mechanism through which I keep putting those charges. Then what will happen then? If I keep putting those charges, then the electrons will try to continually neutralize. They come here, they neutralize, they find more charges, and again some more will come here and then neutralize. Again you put more charges, and then they come here and neutralize. Again you put more charges, they come here and neutralize, and this will go on and on and on. If you keep putting those extra charges on the how you would put it, that's a different story. But you can understand from this that if I keep putting charges on both sides, then clearly what will happen is that a steady flow of current can be achieved. Current can keep flowing because the charges will keep moving. They will try to continually neutralize, because as soon as they neutralize something, then something else is put in there. So they will then some more electrons will flow there, and then they will try to neutralize the positive charge. So they will continually neutralize. So there will be a continuous current now. Okay. Unlike the electrostatic condition. In the electrostatic condition, what would have happened? You put some charges, they go here, neutralize, you're done. No more. No more current will flow. Current flowed for only a very short time period. Now it is not so. You have a continuous supply of charges here. So as these things were getting neutralized, more and more charges were put in here, and the current was continuously flowing. They were trying to continually neutralize. So that's the part we need to understand. So then I can have a steady flow of current. You can use a battery to do it. You can use something else to do it. You can use a generator or something to do that. You can do quite a few things to do that. But the idea is this: if I keep putting charges on the other side, under the two sides now, I can make current flow through this conductor. Okay? So now the electrostatic condition becomes electrodynamic condition. In the electrostatic condition, charges moved and then settled. There was no further movement. But in the electrodynamic condition, charges continually move because you are continually replenishing these charges which are getting neutralized. Some charges are getting neutralized, you keep putting charges. So there is a continuous current that is taking place. Okay. So this is how you move from electrostatics to electrodynamics. Okay. The point to note is, in electrostatics, under the influence of an external field, charges will move quickly and then settle at a place. So that is what is called as electrostatic condition. There is no further current that will happen, and the charges will get distributed on the surface of the conductor. But in the electrodynamic condition, there is a continuous flow of charges, and charges just do not flow on the surface, they can flow inside the conductor also. So the most important distinction you need to remember is this. While in the electrostatic condition, we said that the field inside the conductor is zero. In the electrodynamic condition, when the current is flowing, the field inside the conductor cannot be zero. If it is zero, then the charges will not move from one position to another. So E cannot be zero inside a conductor when current is flowing. That is a very important distinction between electrostatic condition and electrodynamic condition in a conductor. I repeat, in electrostatic condition, charges move and then settle at some positions. No further movement of charges take place. So the field inside the conductor is zero. But in the electrodynamic condition, charges keep flowing. And charges can keep flowing only if there is a field inside the conductor. Okay. I hope you understand this part. I hope you understand this fundamental difference. And you achieve this by continuously replenishing the charges on the two sides. So, as you maintain these charges on the two sides, the electrons inside the conductor will keep neutralizing these charges. As you neutralize the charges, we keep putting the charges. The mechanism, whether it's a battery or something else, that will keep putting the charges. Okay? So this is what you need to understand at a minimum. So we have moved from electrostatic condition to electrodynamic condition. With this introduction, we will get into the lesson. Okay, to summarize what we have discussed so far, electric current I is defined as charge per time. And this works only when you have constant current. In the case of constant current, there will be a constant amount of charge that will be flowing per unit time. So this works for constant current. But if the current is varying, maybe like 1 ampere now, and then maybe like 1.3 amperes a little later, and maybe 1.5 again a little later, and then 0.8 again. So if the current is varying, then the current at any particular point is given by this expression. So I at any particular point in time t is given by the expression delta q by delta t, that is the rate of change of charge when delta t tends to 0. Okay? This is simply dq by dt. Yeah. So this expression is for current which is varying with time. And if the current is not varying with time, then clearly you will get a constant value for this. Okay, for example, if I have this graph, for this let's say, this is time t, and if this is I, it's current, and the current does not change, then notice this, okay, the current is going to remain the same at all times, right? So how will the charge look like? The charge will be like that, T and Q like this. So the dq by dt will always be a constant because it's going to be a straight line. So the slope of the straight line will give you the current. So dq by dt will be a constant here. Otherwise, if it is going to be something like this, the current is increasing, say I and t, the current itself is increasing like this. You see, here you have constant current. Here you have a variable current. With time, the current itself is changing, and clearly the charge will be changing with time like a parabola. Okay, so then when you take that and then when you do dq by dt of that, then you are going to have a straight line kind of a current with a slope. Okay. So the slope of this curve will give you the current at any point in time. Okay, the short point is this. Current is defined as the rate of change of charge. And if the current is constant, then this is the equation you get. If the current is varying with time, then this is the equation you should be using. Okay. And this will give this result when constant current is flowing. It's as simple as that. Okay. And then the second point that we discussed was how to make current flow. So they said I can have a conductor, okay. And then if I have a dielectric here, and I have done dielectric here, two ends, then if I positively charge this and if negatively charge this, then the electrons will start coming towards it, trying to neutralize this dielectric, so they will start moving this way. So electrons will start moving this way now. Okay. And if I keep replenishing this by some mechanism, then electrons will keep moving this way. So I will get a constant flow of current. If I don't keep replenishing this, then what happens is that they come and they neutralize and then they stop. Okay. So that is what happens in the case of electrostatic condition. But here in electrodynamic condition, where you have current and you have to be replenishing these two things constantly. The battery is one such mechanism which does that. Okay. And in this case, E inside is not equal to 0. You have to remember this. In the case of electrostatics, inside the conductor E is 0. But when the current is flowing through a conductor, E inside is not equal to 0. So these are the two things that we discussed so far. Now, let me talk about resistance, because when the current flows through this, then there would be a certain resistance offered by this conductor. We'll talk about the origin of this resistance a little later. But before we talk about the origin of resistance, we'll talk about Ohm's law. Okay, Ohm's law. So when you have a conductor like this, and when current is flowing through the conductor, then what does Ohm's law say? Ohm's law say that the voltage across the conductor, V is the voltage across the conductor. V is proportional to the current flowing through this. Don't take it other way. You can say like current is proportional to voltage. That's not how Ohm's law is defined. Ohm's law is defined like this. The voltage across the conductor is proportional to the current flowing through it. So this, as per Ohm's law, is independent variable. This is a dependent variable. You can give it like that. Okay. So V is equal to a constant of proportionality R to I. Okay. Or V is equal to IR. Okay. So this is Ohm's law. So the important thing to note here again is V is proportional to I, not I is proportional to V. So V is equal to Ri, not I is equal to Rv, some constant interval. Okay. So this is how Ohm's law is defined. Okay. So what is this R? R is called as resistance of the conductor, resistance offered by the conductor to the flow of charges through the conductor. And this again can be expressed like this. R is equal, okay, first of all, this R, this resistance, was found to be directly proportional to the length of the conductor, and was found to be inversely proportional to the area of the conductor. For example, if you have this conductor like this, so this is the length of the conductor. If length increases, then the resistance of the conductor increases, and this is area. the cross-sectional area. The cross-sectional area of the conductor. When I say area, I can take anything, right? So I can take this area also, the surface area of the conductor. I can take this area also, right? But we are not talking about that. We are talking about the cross-sectional area when current flows through it. So if I have a conductor like this, and if current flows through the conductor like this, then I should take this area. But if I have a conductor like this, the current flows through like this, then I have to take this area, this rectangular area that you see, right? So that would be the area you have. Okay. So, but when current flows through this, then this is the cross-sectional area. Current flows like through this like this, then this will be the cross-sectional area. This rectangular thing will be the cross-sectional area. Okay. So this area is the cross-sectional area. You need to remember that. You can't take any area. You have to take only the cross-sectional area. So when I combine these two, then I get this expression R is equal to some constant rho and L by A. And this constant rho is called as the resistivity of the conductor. So this is resistance of the conductor and this is resistivity of the conductor. What's the difference? Well, this is for a particular material, particular substance. If I take copper, copper can have a certain resistivity at a certain temperature. We are not talking about temperatures yet, but let's come to that later. Okay. But copper will have resistivity at a particular temperature. And at the same temperature, gold will have a different resistivity. Iron will have yet another resistivity. So if you make a conductor like this, with these dimensions, with the same length and then the same cross-sectional area, if I use different conductors, if I use aluminum, then I will have certain resistance. If I use copper to make a conductor like this, then I will have a different resistance. And again, if you use iron, yet another resistance. Okay, so there is something about resistance which is dependent on the material that is used in making the conductor circuit. Okay, so that resistance, that thing is called as resistivity of the conductor. So you know that R is equal to rho L A, where rho is the resistivity of the conductor, L is the length of the conductor, and A is the area of the conductor. Okay. So now we have talked enough about this resistivity bit. So what is actually the origin of this resistivity? What brings about this resistance, this resistivity in a conductor is something that we will see now. Okay, I have the picture of a conductor here, and a conductor will have free electrons. We have talked about free electrons before. Free electrons are not excess electrons, but electrons which are not tied to any particular atom. The example I gave you was a child in your street which can go into any house in the street. Okay. At any particular point in time, people who are new to the street may think that the child belongs to a particular house, but it doesn't. Actually, it belongs to a different house, but then it can be moving around. Okay. So like that child, you have free electrons in a conductor, so they will be moving around. And one of the things that makes the electrons move around is the temperature. I already told you that a thermometer is the speedometer for atoms. Okay. We have discussed that in a very light vein in the class. So temperature gives you an idea of how fast the atoms and the electrons, they are jiggling and moving about inside the inside the material. Okay, so the electrons will have a thermal velocity. You have also calculated what that velocity could be in your 11th standard. In kinetic theory of gases lesson, but I'm not going to get into that. But you can understand when I say that the electrons inside a conductor will have thermal velocity. Right now, there are actually, like if I take this conductor, there are electrons here, free electrons here. They are moving about within this conductor. Okay? Right now, because it has temperature. Okay, the temperature means that the electrons are moving with a certain speed. Okay, so but why is there no current in this right now? There is no current in this. But why is there no current in this? Now that is because at any particular point in time, the number of electrons which move in one direction will be equal to the number of electrons which are moving in the opposite direction. So some electrons may be moving in this direction, some may be moving in exactly the opposite direction, and some here, some there, and so the motion of the electrons is random. Why is it so? Because as electrons start moving, then they will go hit the atoms. The free electrons, as they keep moving, then the atoms are fixed, right? So the electrons will go and hit the atoms and then get removed from the atom. Okay, so the direction will change, the speed will not change because the atom is heavy, right? It's much heavier than an electron. Even a proton is about 1,700 to 800 times heavier than an electron. So if you take an atom with nuclei, with its nucleus and the other electrons, clearly an electron is the mass of the electron is negligible compared to the mass of an atom. So you know from your 11th standard that when a light body hits a heavy body, then the heavy body rarely moves, hardly moves, but then this light body gets rebounded with the same speed, the opposite direction. Okay? So likewise, the electrons will go hit these different atoms and then they get rebounded. Okay? So the direction will change while the speed remains the same. So they will move about there. So if you take a conductor at any point in time, there will be almost approximately equal number of electrons moving in one direction and the opposite direction. So resulting in no net current in a conductor like this. Right now there is no net current. But then when I apply a potential difference across the ends, which means that I am setting up an E inside the conductor. If I keep setting up, if we maintain that E, as I said, by constantly replenishing the charges here, by using a battery or something, and if I maintain that E, then I can have a steady current. Okay. So the electrons will also move with that speed. Okay, also move because of the speed gained through the electric field. Okay, because you already the temperature is making it move, making an electron move, and on top of it you are also applying a potential across this conductor. For example, we set up a battery like this, and this is my V, and clearly this will set up a current in this, and then this also will the new speed or the new velocity will be added to the old velocity. Okay. So now the velocity of an individual electron, I'll call this as velocity of an individual electron Vi, is equal to V due to thermal agitation, okay, because of temperature, plus it's a vector, right? It's a vector, any point in time. So it's a vector plus velocity due to the current. I call that as the drift velocity. We'll talk about it later. This is the velocity due to the electric field that you set up. So this is a vector quantity and this is a vector quantity, and these two will vectorially add. But you notice here, if this is V, then E will be set up this direction. Which direction? We know that dV by dx is equal to minus E. We know that, right? So clearly, as it is falling, then E will be set up in this. That's E set up in this direction. Okay? So, that's understandable because this is a positive, this is positive, this is negative. So, if I keep a unit positive test charge, it will go from this place to that place. So, E will be in that direction. Okay. So, the electrons will start moving in the opposite direction because they are negative, right? So, the electron is the direction of electron. So, I will call this as Vt. So, electron will move in this direction with speed Vt. Okay. So, what is the average velocity of an electron in this direction? Well, it will be 0 because due to this one. What would that be? It is going to be 0. Why? Now notice here, what is the average V of an electron is equal to velocity of the first electron, velocity of the second electron, and then the third electron up to here, and the velocity of the nth electron here. So divided by n. But we know this. What do we know? We know that on the average, these things will sum up to 0 because you take one electron will move in this direction, another electron will move in that direction, and this direction. All kinds of motion is possible because of the thermal agitation. Okay, so electrons are moving right now, but then they are moving randomly. So since they are moving randomly, then what would be the average velocity of an electron? Okay, that is going to be equal. We'll call this as Vi. Okay, that is going to be equal to 0. Why? Because this sum is equal to 0. So this will become 0. So Vi, VIT, okay, call it as V1t, V2t, V3t, and VIT. So effectively it will be 0. So what is Vi going to be? So Vi is going to be equal to this Vd, because that's going to be 0. Okay. Then how do I calculate this? Well, I'm going to the electron is going to move in this direction, but E is set up in this direction. Okay, and this conductor may have a length L. Okay, this conductor may have a length L. We know that voltage V, this is speed, I'm just talking about voltage V, is equal to E into T, in this case, right? So E is set up there, there is an E there, so E is in this direction, and that is going to accelerate this charge. Okay, this is a constant, E, it's an E L. So V is a constant and L is a constant, so E will also be a constant. So E is set up in this direction. So the force experienced by the electron, Fe is equal to E into E. Which direction? Opposite direction. Because E is in this direction, electron is going to be pulled in this direction. The direction opposite to the direction of E. So F is equal to minus E to E, capital E into E. That's the force experienced by it. And if there is a force, then there must be an acceleration for the electron, right? Okay, so how do I calculate the acceleration of the electron? Fine. So this acceleration of the electron is equal to force of the electron by mass of the electron. Why? Because Fe is equal to me into A. So that gives me minus E by m, where m is actually the mass of the electron. Okay, I can even drop the substitute E, but I just keep it for the time being. So E by this is charge, right? This is charge. Charge is equal to field into charge. So I'll just keep m, not confused. So this is E and this is capital E, and then this is mass. That's the acceleration of the electron. And this is going to be a constant acceleration. Why? Because the field is constant. Why is the field constant? Voltage is constant and the length is constant. So E must be constant. So you have a constant acceleration. So in the case of constant acceleration, then those three formulas that you learned in the 11th standard for uniform acceleration should be applicable here. So what do you think will be the speed? The speed is equal to, I am going to use this expression. Okay, remember this formula, V is equal to U plus AT. U plus AT. So what I am going to do here is just that. So the electron will get accelerated. So the electron is there, it's moving somewhere. And now the field is trying to accelerate it in this direction. The speed will go from 0 to some value. And then the electron goes and hits an ion, okay, an atom. Okay. And atom is ionized right now because it has lost an electron, right? So electrons are, some of the electrons are freely flowing in the conductor. So the atoms are actually ions. But then I'll use the word atom for the time being. Okay. But realize that they are all, when I say atoms, they are actually ions because they've lost one of the electrons of the atom is free in every atom, or one or two, depending on the material. So the electron that is getting accelerated will go and hit this. Okay. And as it hits, then it will give its energy. Okay, make its juggle, and then it will come back. It will stop. Okay. Then what happens is that again the field is going to accelerate it further in this direction. As it tries to go this way, it goes hits and then it tries to go this way. But the field is trying to still send it in this direction. Or in this case, it sends it in this direction. So it gets accelerated, it goes hits an atom here and tries to go there, but then E is trying to send the electron again in this direction. It keeps pushing it that way. Okay. So what is the speed it will reach? And that depends on the time over which it is accelerated. Right? It starts at 0 in this direction, then gets accelerated, it collides, and then again it accelerates, and then it collides, accelerates, collides. Okay, then, right? So the same thing, this happens continuously. So if I take the mean time between collisions, that is the speed. It will, using that I can find the speed. The electron will reach. So this is AE, and if I multiply that by the time, this is tau. I'm going to use tau, where tau is called as a relaxation time. Okay? The tau is called as a relaxation time. So why is it called as a relaxation time? Because it is a time between collisions. It collides, relaxes, and collides again. Okay? And again, relaxes, collides, relaxes, collides. So the time between collisions can be called as a relaxation time. Okay. So that is tau. So this is acceleration, and the speed v is going to reach is actually this acceleration into the relaxation time. U is 0 in this direction, right? In the direction of the field. So that gives me minus small e, capital E with a vector, and then m and then 2. That is B. But that is actually VD also, right? So that is actually VD. That's VD. I can treat this as VD. So that is called as VD is called as the drift velocity. Okay. So this is the speed with which the electron will move from one place to the other. Okay, so it will start, it's kind of an average speed with which it will try to go from one end to the other end. It will reach this speed at some point in time. It's an average speed. Okay. Some electrons could go a little faster and some can go a little slower, but this is actually the average speed. If you take a random electron and that electron, you can say it's going to go with this speed. It's the average speed of the electron. So it's called drift velocity of the electron. So when you apply a potential across the two ends of a conductor, you are setting up a field, and then this field is going to drive the electrons to move, the free electrons in the conductor to move. And the speed with which the electrons will move from one end to the other end is given by this expression. So minus E m by t. Okay. Yeah. Hope this is clear to you. So we have calculated the drift velocity to be this. So Vd is equal to minus E by m to 2. So this is with the direction. Okay. When you are mentioning the drift velocity as a vector, and this is what we'll be using. And when you use the drift velocity only for magnitude, then the minus sign and then all the direction thing will go off, and simply the magnitude of Vd is going to be equal to E by m to 2. So that's understandable. I don't have to explain, but anyway. Okay, so let us see how we can connect it with the current which is flowing through the conductor. Okay. So let's say let me take conductor like this. We said E is applied in this direction, electron is moving in this direction, Vd. This electron is moving in this direction. Okay. And we said L is the length of the conductor. Length of the conductor. Okay, what do you, how can I find the current through this? Well, I can do this. Okay. Let us suppose that it is, I know this number, when n is a number of free electrons per unit volume of the conductor. So usually this is one number for one particular material. Copper will have certain amount, a number of free electrons per meter cube. Okay. So something like that. Iron can have different numbers. So but I know that I know what material this is, and I take this n for that material. So number of free electrons per unit volume. Okay. Then how many electrons will be here in this volume? Suppose this is A. The cross-sectional area is A. So what's the volume of this? The volume of this is actually volume is equal to cross-sectional area A into length L of the conductor. So how many charges are there in this volume? Well, I know n, which is the number of free electrons per unit volume, and if I multiply this number with unit volume, then I will get number with this volume of this conductor. I will get the number of free electrons in this volume. This is for the material, copper or iron or aluminum or whatever, and this is for this particular piece of that material. Okay, so how much is there then? Okay, the charge contained in this is equal to N A to L into E. Okay, so this total number is capital. This is N. N into AL is the number of electrons, and then E is the value of the charge. So the total charge contained in this volume is given by this expression, Q is equal to N AL E. Okay, that's fine. Okay, now, so this is the total amount of charge in this, and we know that every electron on the average is moving with this speed. Okay, so what is the time, what is the current through this? What is the current through this area? I need to find out the amount of charge it goes, amount of charge it crosses this area, and how long it takes to do that. So I'll start from the first electron, then second electron, third electron, fourth electron, fifth electron, sixth electron, finally the last electron. So how many electrons have gone? Okay, so many electrons, NA electrons have gone. So how much charge is gone? This is the amount of charge that will leave this. And what is the time it takes? That is the question. Okay. How do you find the time? First of all, let us suppose that the first electron is here and it has slipped. And second electron will leave, third electron will leave, it's okay. But if I take the last electron, this last electron will take a certain amount of time to leave this. Right? So you start with this electron, the first electron, that is when you start the count. And then the last electron leaves, and that is when you stop the count. And within that time, how many electrons have left? All the electrons in between, right? Which is this, NaL. The number of electrons is this within the conductor. So many electrons would have left. And the amount of charge that is left is this. I hope you understand this. Okay, so what's the time it takes? Well, the time it takes for all these charge, all these electrons to vacate this place is what? It is this. Okay, how long will it take this last electron to cross? Well, the velocity of the last electron is Vd. Okay, the average, and it needs to cross a distance L, and then it will take certain time, right? It needs to cross this distance within this time. So then what is the time for the last electron to move? That's the time it takes for all the electrons to leave, right? So I start with the first electron, then I see when the last electron leaves. The last electron leaves at this time, delta t, because it has to cross this distance length, L. So delta t is actually equal to L by Vd. So that's the time it takes for all this charge to leave this conductor. So what is the amount of charge that has crossed this area, this cross-sectional area? Amount of charge that has crossed is this. What is the time it has taken for them to cross the area? This is the time it has taken. So can you find the current? Yes. So what's the current? The current is equal to Q, or change in Q, by delta t. The time it takes to cross that. I started from zero charge, and then I ended with so much charge. So my delta Q is actually this. Okay. So that gives me N A L E, okay, by what is delta T? L by Vt. So it will go up. So N A L E Vt by L. So this will go away. So the current through the conductor can be given by this expression, N A E into V D. Yeah, that is it. That's a very easy way to remember this. If we rearrange this, it will look like I is equal to V E N A, Vena. Okay, I can write this as I is equal to V E N A. V is actually V D. So I is equal to Vena is the expression for this. That's the amount of current which is flowing through this. Okay. So hope this is. Well, if I calculate the current, then I can calculate the resistance. Let's see how to do it. We know that V is equal to I into R. Okay. So what is V? V is actually E into L. So right. So if you have a conductor like this, and I apply a battery V process, I'm going to set an E there. So this is going to be the length of the conductor, and E into L will give me V. So V is equal to E into L. E is equal to L. Okay. So this is equal to I. So what is R? R we know to be rho into L by A. Okay. So L and L will cancel. So E can be written as rho into I by A. So what is I by A? Current through the area. That is current density. That is J. Okay. Can also be written, E can be written as rho into J. Okay. So we take this. Rho doesn't have direction, but then J will have direction. So this is what it is. I can write this as rho into J. Or I can write J as this E by rho resistivity. That can also be written as conductivity. 1 by rho is conductivity into epsilon into E. So I can either write it like this: E is equal to rho J, or J is equal to sigma E. Okay. So this is a possibility. These two expressions can be derived straight away. Well, let's try something else here. Okay, I'm going to use this and find rho. What is E? E is equal to rho I by A. But what is I? Is said, right? I is equal to Vena, VD, E and A. We just derived it. So let me put it there. So this is equal to rho into V, drift velocity of the electrons, E N A divided by A. This and this will cancel. So what I got here? I got rho VD into E N equal to E. Okay. I'm not going to stop with it. I'm going to use this expression for Vd. What was the drift velocity we found out? Vd is equal to E by m into tau. Right? That's what we derived a short while ago. I'm just taking the magnitude alone. I'm not considering the direction. So Vd is equal to E by m to tau. So if I were to use it here, what I'm going to get? So this is going to be equal rho into E by m into tau. That's for V, and then E, and then n. So this E and this E will cancel. Can I find rho from this? So this is 1. So rho is going to be, this is 1, right? It's going to be m by EENT or I can say E squared n tau, or better I can do it like this, m by n e tau, neat, m by neat. Okay, it's very easy to remember. So rho can be written as m by neat. So this is a relaxation time. Tau is the relaxation time, rho is the resistivity, m is the mass, n is the number of electrons per unit volume in that material, then E is simply the electronic charge. So N E squared tau, or mc divided by neat. Okay, that's very easy to remember. So that's the rho. So you can understand a few things here. Okay, so rho, if you see, the resistivity will be small. M is constant, that's mass of the electron, it won't change. E will also not change because there is a charge of the electron, that also will not change. What can change? N can change, and then tau can change. What is N? N is the number of free electrons per unit volume. Okay, that depends on the material. Copper may have one N value, and iron may have a different value. So it depends on the material. So if that N, if the number of free electrons per unit volume is more, then clearly resistivity will be less. Okay, because it's in the denominator. Also, if tau, the relaxation time, is small, that is, the collisions are not that frequent, then rho will be small again. Okay. Or when would rho be high? When the collision time is less, right? Or n is less. But let's talk about collision time, tau. The relaxation time. The relaxation time is less, it's okay. Which means that the collisions are happening too frequently. Okay, so particularly like if you heat up something, okay, at higher temperature, what happens is the electrons will move pretty fast, so they will collide very quickly. So they will not have relaxation. They will have a very small relaxation time because of the frequent collisions. When the temperature is high, I hope you understand this. When the temperature is high, electrons will move fast, and the collisions will be more frequent. The collisions are more frequent between the electrons and the atoms, then the relaxation time is going to be smaller. The time between collisions is going to be smaller. If the time between the collisions is going to be smaller, then resistivity will be higher. And that is why, as temperature increases, the resistivity of the material increases. Okay? And that is why when a material has more number of free electrons per unit volume, then the resistivity of the material decreases. So this gives you an idea as to how this thing works. And from here, I can also find conductivity. Conductivity sigma is simply 1 by rho. So that gives you NE neat by mass. So that's it. So we have all these important equations. E is equal to rho j, and then j is equal to conductivity into E, and rho is m by neat, and sigma is neat by m. And I is equal to Vena, and Vd is equal to E m into t. So this is the acceleration, simply the acceleration. Remember, this is a force, E into E divided by mass, that gives you the acceleration, into time will give you the speed. Uniform acceleration to that relaxation time. So you get this relation. Hope it's clear to you.